Good afternoon, everyone. Let's look into how we can design the bolt for strength. Now, bolt in shear, that's a clause now from 9.2.2.1 of AS 4100. And what it says is that when the bolt is subjected to shear, we have this basic equation in the design, where if you recall, as I've said, the left-hand side is the applied shear force, that's why it is VF star, which must be less than equal to the capacity or the nominal capacity of shear of the bolt. Now, the nominal capacity of shear, you can see BF, and then it is multiplied by the capacity factor 0.8. Okay. Now, the VF, which is the nominal capacity of shear, is actually given by this expression. Now, this is in this expression, only in this 2020 version of the standard, we have this KRD added. All other factors were there before. So what are those? If you look at this AV, which is the bolt shear area, and which is comprised of two terms, the first term and the second term. Now, what is the first term? It says number of shear planes with threads. That means what happens is that when the bolt is this, that not every part is threaded. So it can happen that the shear part is actually cutting the portions where there is no thread and the another portion where there is a thread. So there is a distinction between these two. Okay, because why there's a distinction? The reason for the distinction being that the capacity can vary whether the shear plane intercepts the threads or intercepts a cross section which is without the thread. Okay, so that's the distinction, and that is the reason that because there is a difference in the capacity, we have distinguished or differentiated between the shear plane cutting the threads or intersecting the threads or not cutting the threads. So NN, number of shear planes, excuse me, with threads intercepting the shear plane, and AC is the minor diameter area of the bolt. Now, these goes together. Together means NN will be associated with AC from table 8, AISC, and then NX, which is the number of shear planes without threads. You see, this was with threads, this one without threads, and then we have this A0, which is the nominal plane sank area of the bolt. From table 8. We look at the table 8 in a minute. So these are the major contributors. That means this is in fact, these two actually contributes to what is called the bolt shear area. Okay. Once you have done that, then you look at other terms, which is your KR, which is the reduction factor from table 9.2.2.1. It is to account for the length of a bolted lap connection. Remember, this is only for the lap connection. If you have other types of connection, then this factor will not, will not come into picture. That means it will be 1. For other connections, as I have said, it is 1.0. Now, the new factor which is introduced here is in the standard is KRD, which is a reduction factor only for grade 10.9 bolts. That means it is not for 4.6 or 8.8 grade bolts. Is a reduction factor for high strength 10.9 grade bolts for the reduction of ductility, and for grade 4.6 and 8.8 bolts, KRD equals 1.0. So if you look at the standard, it is what looking at the standard when you are studying these models, because you see that there are more information. For example, it says, the standard says that the KRD, when you have 10.9 bolts where the threads do not intercept the shear plane, it is 1.0. But where threads intercept the shear plane, there's a reduction in the capacity and the factor is 0.83. Okay, that is from this clause 9.2.2.1. So this is your shear capacity, and then what we are doing, we are multiplying by this factor. Now, what is FUF? It is the minimum tensile strength of the bolt from table 9.2.1. So that means that's the tensile strength. Then you are multiplying by 0.62, and that's the factor which, and in fact, 0.62 times FUF is the, you can call it as the minimum, shear strength of the bolt. That's the factor. Then you multiply by the factor 5, which is the reduction factor, or I would say the capacity reduction factor, which in this case is 0.8. Now for the reduction factor, it is important that you look into, I think it's look into table 3.4. Please, let's go back. Yeah, it is your table 3.4. So that's the factor of 5. Okay. So let's now move on. Now, if you look at bolt intention, which is the next clause, clause 9.2.2.2, then NTF star is less than equals in 5 times NTF. Now, again, the same kind of expression, but only in this case, it is written in terms of the tension. NTF is the nominal capacity of tension, which is given by AS times FUF, and AS is the tensile stress area of the bolt. Okay. And the above design of bolted connections can be conveniently done with the aid of AISC design capacities, because we have the design capacities in table 9 and 10 available on the study desk. So one can actually use that design capacity table and design them. Okay. So this is another approach of designing. Okay. And so the important thing is, now if you look at here, this is much more straightforward compared to shear, because AS is the, the cross-sectional area and the tensile stress area multiplied by the nominal tensile strength. So that's much straightforward how to estimate the nominal capacity of the bolt in tension. And then you can see the applied tension force must be less than equals the nominal tension capacity of the bolt. And remember, it is multiplied by the capacity reduction factor. Now, table 8 from AISC, that's the design capacity. Now, in this case, I've taken from the handbook. That's fine. It's there also the design capacity book. Now, if you look at the left-hand column, it is the nominal diameter of the bolt from 12 to 36. And that's the designation. As I've said before, it's always designated by this letter M. And then these are the different areas. When you have the core, that means when you have the thread. Suppose when you have the thread, that means the shear plane is intercepting the thread. You can see there's a reduction in the reduced cross-sectional area. But on the other hand, if it is intercepted by a by the bolt where there is no thread, okay, that means without the thread, that means you can see the shank area is much higher. So you can see that why there will be also difference in the difference in the strength, isn't it? That's why it is important that to distinguish and then count them correctly and then estimate the capacity. So that this is for the core where we have the thread, and then this is the shank where you don't have any thread, and this is for the tensile stress. Okay. Now this is table 9, which is basically taken from this the design capacity table. So if you look at the table 9, it's for 4.6 snug tight bolting category. FUF is 400 APA, 50.8. And then you can see that depending on the diameter of the bolt, this table shows us the actual tension capacity of the bolt. So it directly tells you, what's the tensile capacity. And then if you look at these two columns, they are basically your shear values, right? But remember, this is giving in single shear. That means only one intercepting one plane. So threads included in shear plane, this is the capacity. Threads excluded from shear plane, this is the capacity. Obviously, you can see that the threads excluded from shear plane, the capacity is higher. And it's quite significantly higher in some of the cases. And not some, I would say almost all the cases, you'll see that there's a significant increase in terms of the capacity when threads are excluded from shear plane. This is an important point to note. Now, what actually happens is, if you look at the note, excuse me, it says, bearing or plate tear out design capacity for all reasonable combinations for ply thickness, bolt diameter, and in distance, the design capacity for a ply and bearing exceeds in this case and does not control the design. That means, you see, what it tells you that in this case, it is the bolt, the strength limits. That means the capacity of the bolt that actually governs the design, not the design capacity of the ply in bearing. So it's an important note there. That means if you use a reasonable combinations of ply thickness, bolt diameter, and in this distance, then it is the bolt capacity that governs the design of connections. Now, following on, if you look at the next table, it is the shear tension interaction diagram. Now you can see the vertical axis is the shear and the horizontal axis is the tension. Now, this is very similar to, you can think of, the column interaction diagram, because if you recall that when the column is subjected to an axial load and bending moment, so this is the similar sort of thing. In this case, if the bolt is subjected to shear and tension, that means the capacity of the bolt will be divided between, the shear and tension. Then you have to use this interaction. Of course, in that case, you cannot say that all the capacity will be used in one, carrying one load, for example, shear or tension. So in this case, what will happen? It will be distributed. So that's why we have this interaction. That means if you look at anything, you can see that there are different curves for different diameter of bolts, and there is also threads excluded and included from the shear plane. Now, if you look at any diameter, for example, if you look at M24 diameter, and then if you look at, for example, here, like when it cuts the threads excluded from shear plane. So if you consider that for M24, you have this, the 100 100 kilonewton force, is the capacity or the force, tension forces to be carried. Then you have to move into the horizontal line and then see what is the corresponding maximum shear force bolt can carry. And in this case, you see it is less than 50 kilonewton. You have to interpolate. But you can see that this is basically the shear, the vertical axis, and the horizontal axis in the tension. Remember, while applying the shear or tension, shear tension interaction diagram, it is important that you ensure that the bolt is safe in carrying the shear and bolt is also safe in carrying the tension. Then only you can use the interaction diagram. And in fact, not only the reinforcement column interaction diagram we have looked at, you can also think of that we have also done the steel column. It's not only reinforced concrete column, even the steel column, when it is subjected to an axial load and then bending moment, then also we have seen that this kind of interaction diagram is required. That means we have compression and the bending moment, Now, this is a similar sort of table 10, but only thing is that it is for 8.8 grade. That means we have different types of bolts, whether it is snug tight or, there are 3 types of bolts. If you look at the designation it is called, we have talked about this before, TB and the TF. So one is your friction type bolt and another is bearing type bolt. So you have the TB, which is the bearing type bolt, and then you have the TF, which is your friction type bolt, and then S, which is your snug tight bolt. Okay. So these are the important things to look at. Okay. Now, if you look at here, here FUF is much higher. That's the ultimate tensile strength of the bolt. I'll say the minimum tensile strength of the bolt in this case is 830 MPa, much higher than the 4.8 grade. This is the high strength structural bolts, and then these are the diameters. You can see axial tension capacity, single shear capacity, and in this case, we can see that depending on the thickness of the plate, the thickness of the plate which can, goes with it. For example, if you look at M20, it actually says that if you use a value of your, AE, then what is your, for example, so if you have thickness of the plate as 6 millimeter, and then the plate tear out capacity for that TP and that AE, that means that's your, basically the edge distance, AE, and then you can call it as the, you can see it is 78 kilonewton. On the other hand, if you call bearing in kilonewton for the 6 millimeter plate, it is given by 142 kilonewton. Okay. So you can see that this is very important, and you can also see here 5 values are given, and then what is the ultimate, tensile strength of the plate, that is also provided here. Okay. So it says that the above table lists the design capacity of ply in bearing grade for grade 250, yeah, FEP 410 MPa. For design capacities for ply failures in other grades of steel, multiply the above values by the ratio of the actual FUP to 410 MPa. That means if you have higher grades, you can easily, increase the capacity using the proper FUP. And then we have this similar, the interaction diagram, and it says this diagram is indicative only. The interactive equation should be used for accuracy, CTable 7. So everywhere it's recommended that use the interaction equation. Now let's look into the bolt strength design ply in bearing. So VB star is less than equals 5 times VB. Now where phi is the capacity factor 0.9, VB is the nominal capacity of ply in bearing. Why we are talking about this? Because we have seen that the connection can also fail if the ply fails in bearing. How it can fail? It can actually fail by local failure in bearing, and then also it can fail by tear out. That means it is at the edge, and that's why this A coming into picture. So what are these terms? If you look at TF, which is the bolt diameter, yes, TP, thickness of the plate or thickness of the ply, and then FUP, which is your tensile strength of the ply. See, all these parameters we have seen in previous tables, tables 9 and 10. And then this AE, which is the minimum distance from the edge to a hole to the edge of the ply in the direction of the component of force plus half the bolt diameter, and FUP we know. Okay, so basically what happens is these are the two failure modes. Now, if we quickly go back. So these are the two failure modes, and what you have to do is you determine estimate the capacity in these two cases, and then use the minimum capacity, because that will govern the design. Okay. So if you look at this one, end plate tear out failure, you can see this one, this A1 and A2 are given here. Now -1 millimeter, it is coming from the whole diameter, because the whole diameter is larger than the bolt diameter. That's why this 1 millimeter is here. So A1 is given by this, and A2 is given. You can see this in the figure. This is A1 calculated based on the edge, possible tear out path, and the AE2. So you have calculated both of them and choose the lesser of this value as AE, because that will govern the tear out failure. Okay. Now SP is the bolt pitch, which is basically we call the spacing of the bolts. Okay. And DH hole diameter is DF plus 2 millimeter. That's why the half of the bolt diameter is taken. Now the pitch and edge distances. Edge distance A must be greater than, or it's between 1.25 to 1.75 times DF, depending on the edge condition. Look up table 5.2.2, very important. And then pitch should not be less than, usually it is recommended, not less than 2.5 times DF. Yeah, 2.5 times DF. Now we'll look into another type of failure mode, because the bolts which I have looked at before, they are actually will fail in shear. Now, what will happen is, if you look at the friction grip type of failure modes, that is a bit different type. So what's the difference here? Friction grip bolts are actually graded like this. Now, the design criteria from clause 9.2.3.1, this is the criterion for design. Now, what happens in this case, that the bolt, because we are talking about friction, that means bolt can actually failure by slip. So this is a very important statement. What it says is, failure by slip is regarded as a serviceability limit. You see, that's not the strength limit state. This is a serviceability limit state. As strength is controlled by bearing after the slip. So when the slip happens, that means there's a serviceability failure. We have to still look at that where the bolt fails, considering the strength limit state, and it is controlled by bearing. So the slip load, the nominal shear capacity of the bolt is given by this one. Now that's if you think of a friction, it is a similar sort of, the expression. So how is it? Now this mu, which is basically the friction coefficient, right? So we already know F equals mu n, which is the, the traditional expression of shear force. So we can now look at, in this case, it says mu is the slip factor. If you look at this clause, mu is the slip factor from 9.2.3.2, understood, because it talks about different contact surfaces. That means depending on the contact surfaces, you can have nu. And then what are the other ones? Any one is the number of effective surfaces. How many surfaces are in contact? That's fine. And then NTI, which is the minimum bolt tension at installation as specified in this clause. There's a clause there, 15.2.2. This is the third term. And the fourth term, KH, is a factor for different hole types. That means it also depends on what type of holes. It talks about 1.0 for standard holes, then 0.85 for short slotted and oversized holes, 0.7 for long slotted holes. So depending on the size of the holes, you can have different estimation of the slip load, which is the nominal, in this case, is basically the nominal shear capacity of the bolt. Okay, so that once you calculate VSF, then what we do, we actually check this one. Okay, so we actually say that in this case, when a bolt is subjected to a design shear force of VSF star, it must be less than equals VSF, where this VSF is given by this expression. Now, what it also says is, after designing this one, you have to again use this check the strength limit state separately according to clause 9.2.2. Now, what is 9.2.2? If you recall, that is the bolt subjected to shear. So that means after then again you have to check. See, this is so we are talking about for this kind of bolts, two checks. One is the serviceability check, this one, and then we are also, that means there's a serviceability failure. Then we're also checking using the strength limit state whether the bolt will ultimately fail in strength. Okay. Good.